I'm not going to present me again. So this is an example of one of the materials of the round robin test I have introduced you before. No? In this case, the title of this presentation is Master Curve Evaluation of ANP-5 steel by using these specimens. Right. Okay. Yes. Okay. Thank you very much. The contents of this presentation will be an introduction of the master course, the material we have studied, the results and discussion, the factorial analysis, and finally the conclusions. Okay, I briefly introduced before, the master curve approach was originally provided by Kim. No? This approach is based on the theory that can be described as a free-Whipple parameter distribution and a simple parameter, the reference temperature. So, once you have obtained this reference temperature, you can obtain the master curve for any probability of failure. Being the most common used, the probability of failure of 50%. If you are dealing with other sizes rather than 1T, 1T is 25.4 millimeters of thickness, the master curve proposes a size correction, and you can see here. So the correction converts the actual KGC value into the KGC for 1T. So summarizing, this approach addresses the three main issues when you are dealing with the ductile to brittle transition zone, as are the scale of the results, the dependency of the fracture toughness with the temperature, and the influence of the specimen thickness in the fracture toughness. In this study, of course, the ANP-5 is part of one of the round robin tests of the Franciscus project. This is a modified nickel chromium molybdenum weld material that is representative for an RPV weldment in the first generation of German pressurized water reactors. This material has been fully characterized in previous projects, for example, Charisma or Long Line project. Here we have the chemical composition and the mechanical properties. Here I have just put the tensile properties at room temperature. To obtain the tensile properties for any other temperature, we are going to follow, we have followed the ACTM 1922 that proposed these both equations to calculate the yield stress and the Young modulus. The material was provided by Framatome in as a graph duplex CCA specimen. In total, we have extracted 19 mini-CT specimens with, of course, the geometry I have shown you before, that is the reference for Franciscus project, and of course, being aware of taking this mini-CT from the welded material. The experimental procedure has been developed by following the ACTM 1921, as we pretend to characterize material within the tactile to brittle transition zone. We have performed some tests at the temperature between -88 to -56 degrees. So the specimens were cooled with liquid nitrogen in a climate chamber. The loading rate was 1 megapascal, the square root of meter per second, and the important thing here is we are measuring the displacement in the front face. So subsequently, for the analysis, we had to convert this value into the log line spread. Here you have the results. The T0 was minus 26.9 degrees. Also, we have included two common tolerance bounds, the 95% and the 5%. You can observe that three values were discarded for the evaluation because they were outside the range of the master pool approach, and two values here were censored in this case by the tactile crack growth because it was larger than 0.0 millimeters that proposed the standard. So these values were converted into the maximum uncensored KGC value of the dataset. Here, I'm just taking advantage of this picture. I want to show you the small validity window that we have when we're performing this procedure with small specimens. No? This is because the KGC limit is proportional to the remaining ligament. So, of course, when the specimen decreased, the KGC limit gets lower. So this is very relevant when you are performing this test in order to obtain enough uncensored values, you need to test well below the reference temperature. Recommendations are about minus 30, minus 35 degrees. No? This is something very relevant if you have materials with really low tissue. This is just a couple of examples. You can see the macrographies of uncensored specimen by the tactile group and the uncensored specimen. No? I will show you the fractography later. So I move on. Okay. Here just I summarize the results. We have employed a multi-temperature methodology for this material. We obtained the reference temperature of minus 26.1 with a deviation of a standard deviation of 6.7 degrees. Of course, this material is a well metal, so the result is inhomogeneous. So the important thing here is that the reference value provided by Framatore in this case was a T0 of minus 38 degrees and a deviation of 8.7 degrees. So the difference between our value and the value is 11.9 degrees. Here also it's relevant that they perform the test and we don't have any other reference with 0.37b. To put this value in context, we have reviewed the literature to check the variability of T0 on unirradiated materials. So we compared here the value with GCT and the value with large specimens. Here you can see a huge variability on these relations, and also there seems to be two error bands of minus and plus 12 degrees within all the data points. So also no clear tendency have been found in this review, and here you have our value that seems consistent with the rest of the data. So one important job here is to analyze the fractography of the mini-CT specimens. Because we need to check if the assumption of the master group approach are fulfilled with these mini-CT specimens. I have just put a couple of examples with two different temperatures and two different fracture toughness. The most important thing here is that at the beginning, a small tactile area is present with microvoids, and then the rest of the surface flat. The main mechanism is clear. Also, it's remarkable that here we have some slant fracture at the edges of the specimen, mainly due to the plane stress effect. Okay, another important thing is to try to localize the initiation sites. And here you have the same example that the other slide. The initiation sites are relatively close to the initial crack, no? And here you have the small area of microvoids I talked to you before. So, in general, we have demonstrated that these mini-city specimens are fulfilling the weakest link model because we have only found one clear area of initiation. So, with all this, the conclusions are: the reference temperature was successfully obtained from fracture toughness tests with limited specimens. The tissue value obtained with the mini-city specimens are consistent with those obtained from standard specimens. No clear tendency in Cicero was found in the literature when mini-city and standard specimens are compared. However, the majority of data was found between a deviation of plus minus 12 degrees. The main micromechanism was found was cleavage fracture, which besides accomplished with the link model. That's all for my side. Thank you very much.
Thank you. We are open to questions, please. Yes?
Thank you. I have a question to the requirements for pre-cracking. Because this is, especially for small specimens, hard to fulfill and even more for weld. So my question, did you fulfill the requirements of the ASTM standard for pre-cracking?
Every single specimen will have, the 19 specimens will fit the requirements.
Yeah.
Both the straightness of the straightness criterion and the length criterion. Yeah.
Were there special things you prepared, that some pre-stress or compression during pre-cracking?
No, just the crack length as we measure optically. Yeah.
From your fracture graph, the front, if you look at that, you're talking about fulfilling the criteria for crack front straightness.
Yeah.
It doesn't look like, you can see, it's preferentially going to one side as well. I think that's one of the things you're trying to say. There was no pre-compression, okay. At the same time, what we've done tests on mini-CT exactly the same size. But we've tried to use side grooves. If you can remove that slanting on the side, that's one thing to do.
In practice, we are not using the side grooves because it was demonstrated by the proper invalid that in these really small mini-CT specimens, the impact was very, very few.
But it can help you satisfy that criteria in terms of the crack front straightness. That is one thing.
Yeah.
So my question, sorry if you don't mind, in terms of estimation of the uncertainty, we did share, plus or minus 12 degrees C. Was it a calculated one, or did you calculate it based on the data set? If you look at the conclusion, that's final slide.
That's right.
The final slide, it's there as well, but the final slide is there. So this plus or minus 12 degrees C, is it based on the uncertainty calculation in 1921, or is it just based on that fit?
It's just based on the review of the literature.
Yeah, but what I'm saying, with the ASTM 1921, you need to calculate the uncertainty on your data set. The other thing with the mini-CT was, you did mention, broach it a little bit, because of the limitation, the size limitation, you're limited to a level, that's right. So the closer you get to the lower shelf, not the transition shelf, the uncertainty increases.
Yeah.
So that's the reason you need to quantify that uncertainty and then compare it to for the large specimen size. So there they've said it's plus or minus 8 degrees C, isn't it? If you go back one slide.
That is the graph of temperature against temperature.
No, not that one. If you go on that one, go back.
This one? No?
No, this one.
Oh.
You can see
Okay.
8.7 degrees C. So, did you have a value for your own test? Did you calculate that for your own test?
No.
That's what I'm
It was,
saying.
no. It was provided by Chromaton, so I didn't check it out the data.
Okay.
That's the value they gave us.
Okay. I think you have another question.
my
We still
question-
have time.
My question was answered, it was about the straightness.
No, okay. Yes, please.
Thank you for your talk. I have just one question. Where did you sample the specimens in the thickness position? Is that mid-thickness or top or quarter thickness?
Can you repeat, sorry?
Where did you sample the specimens in the thickness?
Of the large specimen.
Or the small ones?
Yeah. No, here you can check in the figure. Here. That's how we extracted the specimens from the broken one in this area.
What was the thickness position? Because the full
No,
thickness-
in the full, we extracted the specimens in the more or less in the full thickness of the specimen.
Oh, so some of them.
We take a measure of the full thickness of the specimen. Yes.
So some of them might have been on the center line, and some of them might have
Yeah,
been at the
yeah.
quarter thickness
Of
position.
course. Yeah.
And when you got the data, did you separate the ones that came from closer to the surface for the ones which were closer to the center line?
We didn't take into consideration that I don't know, maybe it's relevant, but no, we didn't.
Further questions? Still have some minutes because in the first presentation actually expired.
I have a question. If I understood correctly, you are using a probabilistic model and your variable needs to follow a distribution. Which one?
Here, we are using a few parameter wave distribution.
Okay, and did you check if your data follows a Weibull distribution?
Personally, I didn't check it, but in the literature, I can show you
Yeah,
data.
but you know that, for example, I think that this probabilistic model is based on weakest link principle.
Yeah.
I think you wrote now.
Yeah.
So it depends on a few assumptions that, for example, the distribution must be identically distributed and also independent. So I think that you need to check if your data is according to these assumptions.
Yeah.
Because it's a sort of it's the base of weakest link principle.
Yeah, but that's why we check the factorography. We check to see we encounter multiple site initiations or just only one. And in this case, we have only one initiation area. That's why why I say that we can fit the weak link theory. Because if not, you have encountered multiple sites of crack initiation, you know?
Okay. I think we need to stop now. So thank you, Marcos, again.